Today, 2 talks are scheduled. We have the first pleasure to welcome Professor driscoll from the University of Michigan. We will talk about imaging of turbulent EDs interacting with flamelets to assess concept of dam color and to quantify stretch efficiency. And immediately after, we will hear Andrea Gruber. We will talk about DNS of flame propagation in turbulent boundary layers. Thank you, friends.
Thank you. I want to thank Axel and Niels for inviting me. It looks like it'll be an exciting few weeks. I know some of you, and I'm very happy to meet other people who. This is a great opportunity to meet people who you read about, but you don't have a chance to talk to. I guess I'll start with the experimental side of the discussion this afternoon. Andrea will continue with computations. And let me start with a motivation why we would want to do this. I've already talked to a few people, and the gas turbine engine seems to be a popular topic. We're doing another project on a gas turbine engine, which I will not talk about. But the people at General Electric who are funding this work, they have been developing this lean, premixed, pre-vaporized idea. And the premixing is causing them all sorts of problems. This is something that an engine that's used on the GE for the Boeing 787. It's an engine that's in production, and they gave us one of the fuel injectors. It's a proprietary, top secret fuel injector, and it's this part right here. And this is just one flame tube, and we're burning it at about 5 atmospheres. And the way they get premixing, to my surprise when we started, was they simply get a lifted jet. And so what they call premixing in the industry is to take fuel, shoot it out, jet in a crossflow. The flame cannot stabilize because it's very high velocity. This is a liquid jet A, so it's vaporized. And then we get a premixed, partially premixed flame up here. And then they have a second flame. For safety reasons, they have a pilot flame, which this is pure fuel, but very low velocities, and so it burns as a standard non-premixed flame. And so this flame always goes, and this sometimes jumps around because it's premixed, and it's difficult to stabilize. And this creates what they call the growl. They hear this growl. It's a problem right now. They don't want to admit it, but the ultimate goal is to design an LAS code in this particular industry that is dependable and will compute the acoustics as well as the combustion. And of course, we're a long way from doing that because we have many experts here today that can attest to that. But we are taking experimental data in this device to the unsteadiness, the acoustics, and trying to take the phase average velocity and temperature fields. And there's other work at DLR that's being done very much along these lines. Anyway, that's the last I'll say of that experiment. The experiment I want to talk about for the next half an hour is this one. It's a more fundamental experiment in which we take methane and air, we run it at what we believe is a Markstein number of 0, and so a Lewis number of 1. And so we have co-flowing hot products on both sides, and we get this turbulent flame. And John Bell at LBL has modeled this with DNS. It's simulated with DNS. It's a very simple flame. Now, it's not very turbulent. We call it fully turbulent, but it's not intensely turbulent. It's sort of intermediate turbulence. The velocity fluctuations are about 3 times the laminar burning velocity, and the turbulent burning velocity is twice the laminar burning velocity.
Is it slot or axisymmetric?
But
Is it slot or axisymmetric?
it's 25 millimeters by 50 millimeters long, and so it's
Any confinement?
unconfined. 1 atmosphere. Yes. Yeah. it's kind of loud. It's not a big flame by any standard, but it's turbulent enough that we can say that there is plenty of turbulence in here. But it's not highly turbulent. Now, one of the things that I asked the student, Adam Steinberg, to do is to investigate a couple of hypotheses with his experimental data. And one is, we know, of course, the vortex increases the flame area. This is proposed by Kohler and Shelkin. And the burning velocity might be proportional to the flame area, but we don't know, but it certainly will go up as the flame area goes up. We believe this eddy-flame interaction is important since the days of Kohler. And if you want a good LAS model, you must capture the physics of real eddy-flame interactions. Now, not everybody believes this. If you have a G-equation model, for example, you create a surface that actually propagates normal to itself. You have Huygens principle. You know, it has a wave phenomena. But I think some modeling people believe that statistics will do it, and you don't have to worry about whether it's a wave or not a wave. This is not something I personally believe in. But, yeah.
Okay, the scale of this vortex is larger than the integral scale of turbulence or less?
It's about the same.
So this is turbulent vortex?
This is turbulent vortex. Yes. The turbulent vortices here, the integral scale is about 2 millimeters, and then the Taylor scale is about maybe 1 millimeter, a little less than 1 millimeter. Okay, so these are. It's not very turbulent flame. It's slightly turbulent, but they're integral scale, Taylor scale, and that's what we're talking about. Yes.
For this mix, the typical Reynolds number?
It's based on the integral scale and the mean velocity. It's about 150. It's not. It's a moderate turbulence. The reason is that the laser diagnostics do not work at fully turbulent, high turbulence. So this is the best we can do. Okay. The other hypothesis that Menneveau and Poisson have used in their work is that maybe turbulence is not a single vortex, but it's a vortex pair. And here we have a toroidal vortex that we can slice, and we see a vortex here, maybe it's all connected. Anyway, this, of course, exerts a positive stretch on the flame and pulls it this way and will wrinkle the flame form a hat like this. Well, not all of turbulence is this either, but in the work of Menneveau and Poisson, they assume that all of turbulence is this. And obviously that's a gross assumption, but they simulate this with DNS, and then they do this for many different scales, and they put together what they call a stretch efficiency function. And they're basically assuming that turbulence is a lot of vortex pairs. And wherever the strain is positive, the curvature is negative. So we can identify a vortex pair because the strain is positive. It means we're pulling the flame this way, but the curvature will be like this, and that's negative curvature. And I'll explain that. And the third wrinkling phenomena that we were interested in looking at in our data, Professor Williams will be here, and he has a very nice description in his book of the Landau-Darius instability. I think I'll just say some words about it in case somebody needs to know. The flame has a very large acceleration of the gas in the normal direction, and so the streamlines will be bent and will be pushed away like this. If you look at the tangential component of the velocity, it's conserved across the flame, and so the streamline pattern will look something like this as we go through the flame. So this means in a subsonic flow, the area is decreasing. So this is like a nozzle, and so the gas velocity is accelerating, and so this velocity right here is a little higher than it would be over here. And this higher velocity pushes the flame back because the flame is trying to propagate at the laminar flame speed forward. And so, if this region is pushed up and this region is pushed down, we amplify the wrinkle and the flame becomes unstable. And we want to say, this is well known in a laminar flame, but do we see it in turbulent flames? And so the experiment that I'll tell you about is to take this slot Bunsen flame, achieve good time and spatial resolution, measure all the velocity components, all three, also measure the in-plane components of the strain and vorticity. The strain tensor has 9 components. It's a symmetric tensor, so there are only 6 independent components, and we can measure 4 of those 6. And then, this is what I hope to talk in the next few weeks about to people about. Is when you look at this data, what can we do with it? What's the useful thing to do with it?
Do you use laser Doppler?
No, this is a PIV.
PIV.
Particle imaging velocity.
What kind of CD particles do you use in this?
These are aluminum oxide particles. Very small, 1 micron aluminum oxide particles.
What size of these particles?
What?
What size?
About one micron. About 1 micron. The velocity is not very high here. It's only 1 to 3 meters per second, so the particles don't have to be too small. But then there are optimization to get good light signal.
Jim,
So we have 2 lasers.
Jim,
Oh yeah.
excuse me, I have a question.
Yeah.
In fact, the geometry is not the same for your burner and for the Ponceau burner.
Ponceau burner?
Because Ponceau burner is perpendicular to the floor. In your case,
Yes.
you have some tangential component.
Exactly. Yes.
So it's not exactly the same.
No, it's not the same. No.
How
We did not try to repeat the Ponceau experiment. The Ponceau. No, we will. Okay. So to answer your question, we will look in the data.
Because you have a,
Yeah, I see what you mean. We will look in the data for specific events where the eddy looks like it's. See, the flame is actually like this, but the eddy will come at an angle. So we cannot get exactly this. We can get this.
because the vortices in your experiment live a long time with the flame.
Yeah.
Not like in the experimental.
That's right.
Also,
They're a little bit different.
it's
They're a little bit
completely
different.
different.
So there will be different ones. All we can do is compare, and we get what we have in the experiment. We cannot. But to answer your question, we have these 2 lasers. They are pulsed at 1,100 pulses per second, so a very high repetition rate. And this gives us 1,100 velocity images every second. We have standard PIV optics. The student has a very small field of view, 8 by 11, so it's about a centimeter by a centimeter. Good spatial resolution and sufficient time resolution. Now, Adam Steinberg, now he graduated, he's now a DLR. He's with Wolfgang Meyer, they do perhaps the best work in the world in this general high repetition rate diagnostics. But the first thing we had to do is, how do we identify the flame surface? So here are the particles in the flame. And you can see there's a huge change because the density of the gas changes by a factor of 6, and the density of the particles changes by a factor of 6. We go from reactants to products. So Adam set up a method to look at the gradient in the particle density. And this is standard image processing, but he had to set this up, and then he checked it. He checked it by a calibration experiment, and he was convinced himself that he could track this. And this only works if, of course, the flame is not extinguished. And so he also did some CH measurements. He measured this boundary with the CH fluorescence, and he was convinced that at these low velocities there's no extinction, so the method is okay. So this is what he's done now. What we'd have is a small regions this is 6 millimeters by 10 millimeters, and we have identified some vortex pairs, and vorticity is this way. This fluid is rotating clockwise. This fluid is rotating counterclockwise. The reactants are coming up, and this flame is sort of like this, and these will be going upwards and to the right. And
This is instantaneous picture.
these are each one is instantaneous.
Yes.
It's 10 nanoseconds exposure time,
Yeah,
but then they're taking 1100 per second. So 0.9 milliseconds between the pictures.
Yeah. Have you performed averaging over independent velocity maps in order to see mean
The
velocity?
mean velocity. Yes,
mean
yes.
velocity and mean front.
Yes, yes, he has done that. I don't think I have any data here, but he has done that as well. Yeah. The code automatically does that. Okay, now let me just get this. Let's do this one. Okay, so here is a short movie clip of some eddies going through the flame. And you can see that a wrinkle is developing in the flame. Let me start all over again.
And the flow from down to
Yeah,
what?
yeah. The flame is. This is the bottom of the Bunsen burner. This is the flame, and this is the flame. And these are the reactants, and these are the products.
What's the direction of the flow?
What's that?
The direction of the flow.
The direction of the flow is this way. Yeah, this way. It's a Bunsen burner.
Okay.
Okay.
You have here mean velocity. There is a mean non-zero
Yeah,
mean
yes,
velocity.
this is about 1.5 meters per second right here. And then the gas goes up and then goes out. Yeah. Just like a Bunsen burner.
And is it true that the fluctuation is 3 times larger than the mean?
In the what?
Fluctuations of velocity 3 times larger than the mean. Am I right?
No. The fluctuations are 3 times larger than the
Flame.
laminar burning velocity. But
And
they're only about 10% of the mean velocity. Yeah. It has a grid and but 10% is all he can do. Now what I want to do is show you in this is, okay, now this is first of all, there was a vortex pair, now it's moved up to here. And what we consistently see, this is like the Poinsot, it's like the Poinsot Menneveau idea, except the flame is like this. And there's a velocity component that's added, but everything is there is also a velocity component normal, which is it's like Poinsot.
But much smaller.
Right, that's right. This is much larger. Now, this vortex pair disappears, and we can. Okay, there it is later. It's getting weaker. This is kind of going over. This is not fully disappeared, but it's weaker than it was before. And if I can do this. Okay, this is later. Now we formed a wrinkle, but this vorticity is not the original vorticity, because the red was on top of the blue, and now the blue is on top of the red. So this is new vorticity. So,
It seems to be the vorticity line, these lines are continuous.
yes.
They shouldn't be.
They should be?
Should not.
Oh,
As you showed yourself, the velocity changes, at least the normal velocity changes direction. So the derivative should be continuous.
no, vorticity.
Well,
how
it
do
depends
I-
which direction you
Well, okay, this is the component in. We are only looking at one component of the vorticity.
you have to play data.
Yeah,
Right?
plain data.
So if you have one component which is continuous, that's fine.
You're right.
The other component is not.
In a three-dimensional case, the vorticity lines would be three-dimensional, so we don't see this. All we see is what's. Okay, so when I say vorticity, I mean only the z component, not the other components. These are the contours of a scalar, basically, not contours of a vector. But the wrinkle appears, and so this appears to be like the Manivaux idea, but we don't see this all the time. This is a good one. Okay, there's some bad ones too. What we can measure is this is the component vorticity. We can measure the strain rate SXY by taking these velocity derivatives. And then we can combine these to form, the stretch rate is defined by Candel, proportional to the rate of change of the flame area. And N is the normal to the flame surface towards the reactants. And so we can U is the velocity, and this is now we can get the component of the stretch in the plane of the measurement. Del dot U is 0 because we do this at the upstream boundary of the flame. So if this is the flame, we are making this measurement just at the upstream boundary of the flame, where we have reactants. And del dot U is 0 in the reactants because they're constant density. The density only changes at the flame front.
And what difference? N hat, U vector. N hat, what does it mean?
This is the normal to the flame, so that would be.
But it's a vector also.
It's a vector, but we only have the component in the plane. So N would only have two components.
And vector U is a total velocity field?
No, the definition, it is a total velocity field, but we can only measure
I understand.
the X and Y
Yeah,
components.
but you said that divergence U equals 0, so incompressible case.
Yes, that's a good point. It will not necessarily be 0 in the. Now the flow is nearly one-dimensional. I mean, there isn't any velocity this way, mean velocity this way. So in this experiment, del dot U is in the plane of measurement is approximately equal to the 0.
So U is a mean velocity.
No. In this formula, U is the instantaneous velocity because K is defined at every instant of time.
But you suppose.
But this is only 0. Yeah, this is only 0 if it's done in 3 dimensions.
It's approximation.
Yeah,
Because
approximation.
It is approximation.
And del dot N is the radius inversely to the radius of curvature of the flowing surface too. So these are the things we can measure. And what we observe is that the stretch of the flame increases right here. That's what you would expect. Now the flame stretch is defined as the rate of change of the area in this mathematical sense. And so the velocity field is going like this, right here. And so the stretch is positive. Now the curvature is negative because it's starting to form a little bulge like this. This is defined as negative curvature. And so in the Poinsot-Manivaux concept of a vortex pair, or if we call it Domkohler wrinkling, the curvature and the stretch should be negatively correlated, and that's what we see. We see the vortex like this, stretching the flame and forming a wrinkle like this. Okay. Now, later on, though, this vortex becomes weak, and what these two quantities look like they're positive correlation, and that's the Landau instability. In other words, there's no more vortex. Here the flame is wrinkling all on its own, and it continues to get more wrinkled all by itself. So the vortex creates a small perturbation, and then much of the wrinkling is done by this mechanism. So there are two mechanisms that are important.
So, can you just show us again the expressions, how to evaluate both the stretch and the...
Oh, yeah, we'll go back. The stretch, we go along this line in front of the flame in the reactants, we compute the normal vector in the plane of the measurement.
Okay, I understand. Yes, thank you.
And then we take the derivatives of and we have u and v at every point. So we just go right along this line, and we get a number that is only a function of the distance along the plane. Okay, it's a little confusing because
But you neglect all time by the third component of the velocity.
what's that now?
By third component velocity, you neglect.
We don't get that. But what we do, we compute all of these quantities, including del dot u, but using only two components. And if we had more time and more money, we would try the third component, but we haven't done that.
But you can say this is the curve straight in the given plane. So
Yeah.
it's
Well, we have the third component of the velocity. We don't have the d by dz. d dz. We can't get that. Because,
You have to slide,
Yeah.
you
yeah. We have to have two sheets.
have to shift.
Professor Dom, who I work with, he has a system that will do that, but he's doing something else with it.
You could, just a comment, you could estimate the relation term by looking at, if you know the density changes, you mentioned was factor 6. So you could use the
That's true.
zero dt over one of the rows.
That's true. We do know the density change. Yeah, we do. That's an idea. Maybe I'll think about that. That could help because we do know the density change.
You need time to read with that.
Now, what Adam did for his thesis, he just looked at this data, and here are a couple of good examples. Again, these are probably the better examples. Not everyone looks this good, but these are measurements at different times in the turbulent flame. And this is the theory that's in Professor Williams' textbook. And we see flow patterns that look very similar. This is now at a later time when the vortex is gone. There's no vortex here. It looks like a Landau instability. Okay, and so to summarize these measurements for this part, there's a negative correlation between the strain and the curvature, which is predicted by the Domkohler-like wrinkling. And then at a later time in the wrinkling, we see hydrodynamic wrinkling. And so it's clear that both of them are present. And so if you were developing a large eddy simulation, many people ignore this part of it. And I think Ken Bray has done some nice work where he has added it, but there aren't too many other people who can talk about that. But it's clearly observed in the experiment. The other point is that flame generates vorticity, and this is this point where we have this vortex pair, red and blue, red and blue, red and blue, and then later on we see blue on top of red in the products. And this is because vorticity is created at the flame front. The original vortex is totally destroyed, but then new vorticity is created in the opposite sense. And this has been predicted by a baroclinic torque term in the vorticity transport equation. In fact, again, Foreman has done some work on this and others. And actually, we did some experiments with a laminar flame vortex, where we saw this. And so it's not too surprising now when we go to turbulent flames, we see this. It can be explained by the transport equation for vorticity. The original vortex expands, though its volume increases by a factor of 6. And so even if its angular momentum is conserved, the vorticity will go down as the volume goes up. So this vortex, as it goes through, it expands and it's destroyed. And there are viscous forces in the flame that will destroy the vortex. But then there are new velocities that are created at the flame front, and they create a rotation that's opposite.
That rotation is the non-alignment, because non-alignment of density gradient and pressure gradient.
Exactly,
So,
exactly.
Now, you can see the pressure, I suppose, doesn't change.
The pressure field.
Yeah, but the density will change, of course, a lot.
Yes.
It depends, it's just normal to the surface.
I believe so, yes. I believe so. I'm not.
That's why it probably gives you the change in the direction.
But,
Jim,
yes.
one thing, I don't understand exactly. In fact, lambda instability gives you some vortex, kind of flame.
Yeah.
But what is the transformation of the length of this vortices? Because
Yeah. Yeah.
Landau instability chooses some
Flame
scale.
thickness is the.
But after, how we obtain the big vortices? Due to what mechanism?
Well, that's a good question.
You-
That's a good
You
question.
told that we have a small wriggles.
Right.
And how small wriggles,
Yeah.
it's not real turbulence, it's an inverse process. So
Uh,
how do you describe it?
That's right. In the Landau instability, the only length scale is the flame thickness.
Yes.
But
You obtain big
But we
scale.
also, in this real experiment, we have perturbation. The original perturbation has a certain size to it. So apparently, it's not just pure Landau. The perturbation has a size, and then the flame-generated vorticity appears to be about the same size as the perturbation.
But what is the mechanism?
Well,
Because
actually,
you-
I don't know.
Because you wrote before it's a small wriggles, and
Yeah.
you have a big wriggles.
Yeah.
How?
Well, the mechanism is, as it was pointed out, the density gradient and the pressure gradient are not aligned.
But you have the curvature
This
that
creates-
steps in.
Yeah.
So you have another length scale, not only the flame thickness, but the curvature. That's gives you the,
Well, yeah, but that's right.
or the length size.
What's the nature of the original turbulence before that Landau instability arrived? What's the nature? It's some kind of shear turbulence introduced turbulence, initial turbulence which shear produced.
Yes,
So in some sense you've got combination of several mechanisms.
that's right.
Yes, it's, of course it's some
Yeah.
not so simple interaction.
Well, in the experiment, the size of the vortices is very important. The integral scale, because that's what perturbs the flame.
But why I pose this question? Because in LAS, you propose all time there is some cascade from big vortices to
Yeah.
small vortices.
Yeah.
But here they observe other thing, in
Yeah.
other direction.
Yeah.
So how we can apply LAS to describe this
Yeah.
kind of its inverse sense?
I don't know. I think we still need to.
This is the problem for LAS.
Isn't it because of the expansion? Isn't it because of
No,
the
it's
density?
not expansion, no.
There is a substantial density change from the one point to the
For me,
bottom.
it's not, because even if Landau works, we have to do this process from small vortices to ground to big vortices.
But if you take
It's
into
not,
account,
it's not just this process.
if you resolve energy contained scale, you can reproduce somehow large scale instability. Because large scale instability, we can think that it's a result of averaging or something. And if you resolve this scale, why not
The name you call that hydrodynamic wrinkling is maybe slightly misleading, perhaps,
Yeah.
because it's really from the feedback.
So you have
Yes.
It's a feedback. So
Right. It's at later times the hydrodynamic phenomena we believe is occurring, but it's combined with much more.
yeah.
So it is not a pure hydrodynamic wrinkling. I think maybe that's what the issue is.
Yes, it's really.
If a flame with no turbulence at all, this is a laminar flame, as we know, will wrinkle,
Mhm.
Yeah.
but it will have a certain scale that is maybe 5 or 6 times the laminar flame thickness, right? And we know that because Kobayashi did some excellent work showing if you do this at high pressure, you get very tiny wrinkles. You do it at low pressure, you get big, fat wrinkles. Yeah.
So if I looked at turbulence without any flames, one would then probably see, and I'm asking here, anti-correlation between stretching and
Mhm.
curvature. Is that right?
Yeah.
So
Yeah.
therefore, a purely hydrodynamic process would be
Mhm.
whatever you don't call hydrodynamic in this case. So therefore,
Is due to turbulence. Yes. Yes, and so everything is coupled. There's no pure hydrodynamic instability. It's coupled with the.
We know the experimental data, very famous from Russia, it's a Gostinцы. We know the it's a spheric flame.
Yeah, oh
And
yeah.
a quiet flow.
Spherical flame,
So
yeah.
you have a continuous development from small vortices to big vortices.
Yeah.
So it's the same heat release all time,
Yeah.
but you have more and more vortices.
Yeah.
So how you can calculate this?
But this has a forcing function though, Vladimir. These are always being forced by forcing from these eddies here and have a certain size. And I think if you always are forcing it, you will get eddies of a certain size. That's what we do.
But not clear.
Yeah.
Jim,
Anyway, I'll just show
Jim,
a few
quick
more.
question.
Whoops.
can I ask you a quick question?
Yeah.
So just as hot exercise, if you do the similar experiment with a passive scalar,
Yeah.
which is not altering the dynamics, would we expect to see the same negative correlation between the stretch and the curvature?
No, I think almost everything that we're seeing is due to the propagation of the wave. It's a wave phenomenon, I believe. The hydrodynamic instability clearly is, and the interaction of the eddies in the vortice. In other words, if we did this even for different laminar burning velocity, we might see something very different. So, and a scalar would have zero burning velocity. So, no.
Because the isoscalar surfaces are going to be stretched on the contorted.
That's true.
Very
That's true.
Yeah, and then I think, according to what you're saying, you would expect to be on the left of this first plot which you showed, where you had this first increase of the correlation from negative to positive values and then the flatter scheme. I think for passive scale, you would be on the left of this
Yeah.
graph.
Yeah.
And that should be checked.
Yeah.
And you also don't know that.
I do know that, well, I do know for a fact that when you look at Werner Damm's measurements, he has some scalar measurements. He doesn't have the velocity, though. You know, what you're talking about is velocity and scalar. He has just scalar, and this surface is extremely wrinkled. There's no limit to how wrinkled it can be. It can become fractal. With a flame, it never gets very wrinkled because the heat release. It's heat release. It's like, I think in some of the old Russian literature, they talk about jets of fluid coming out like a jet. So if you try to wrinkle it too much, the jets prevent it from wrinkling. But in non-reacting, it can wrinkle like a fractal. That's good for us because we don't like a lot of wrinkling. It makes us life difficult. Anyway, I think I'll just finish up. We have other movies here. Sometimes we see very complicated patterns which don't look at all like. Let me just stop there. You know, sometimes we see many vortices that are very close together, and so the pictures I've been showing up to now, they're the best ones. Lots of other cases we see very complicated multiple eddies, and it's hard to make sense out of that. You know, there isn't any vortex pair or a single vortex, and so one thing that Adam did was say, well, maybe we shouldn't be looking at vorticity. We can measure the strain rate in the fluid, this S quantity, directly from our measurements in the plane of the measurement. And you see, if you have a theoretical vortex pair, the vorticity is here, but then where the flow is going like this, you have a very high extensive fluid strain rate, and here you have a very high compressive strain rate. What if we start looking at these structures instead of these structures? And this is the same data, but now we're looking at contours of the strain rate. And you see strain structures, and they look different from the vortex structures. Now, if you just had a single counter-rotating pair of vortices, then it wouldn't make any difference. The strain structure would be here, and the vortex structure would be here. But if you had lots and lots of these all together like this, then of course it doesn't matter if the vorticity gets close to the flame. What's important is the strain in the fluid, and that's what defines the strain on the flame. So the approach was to look at these strain structures, and what Adam did was he tested out this idea that maybe the vorticity wrinkles the flame but doesn't stretch it so much. And let me go back to this example. If you had a solid body rotation, you have vorticity but no strain. Okay, this is a classic problem. And if this vortex pair was to interact with the flame, you have to define where is the end of the flame, here and here, but they'd be pulled inward. And so the total area from this mark to this mark is the same as from this mark to this mark. So the area of the flame has not changed, but the wrinkle has been produced. That's the theoretical solid body rotation. On the other hand, you can have a counterflow flame where you have no vorticity, but you have strain. And so that's a different velocity field. We can write this mathematically and show that these 2 points will now move out to here, and there's no vorticity. So the idea is maybe we should be looking at this data in terms of vorticity or strain, depending on what we want to look at, what we want to understand. And it appears that this saying is approximately true, that the vorticity field tends to wrinkle the flame, but it's the strain structures, which are somewhere else, which tend to strain the flame and increase its flame area. Okay, and so here's the strain field, and here's a strain field in which the flame is just pulled, it's just pulled, but there's no wrinkle. It's just stretched, it's just elongated without a wrinkle.
Is it observation?
Does it?
Is it observation?
Yeah, this is from the measurement. So I think we have to be a little careful when we develop models. Vorticity is not the whole story; it's the strain rate that's important. And the last thing I'll say is that we can, from this data set, we can measure this mean stretch rate and see what it correlates with. Because in a subgrid model, in LES, we want to know what is the stretch rate on the flame surface, because we cannot compute it. We have to.
I don't understand.
Yes. Yeah.
In fact, you show that if you have just stretch without vorticity, the flame is extended like that, by the flame surface is not changed. You have a flat flame without change of surface.
No, the flat flame did change the surface. It did change. Back here?
For me, it's like if it's up to infinity, it's the same.
Well, this is a counterflow flame, and it is strained.
For example, we have the flame in the stagnation point.
Yeah.
I don't observe the change of velocity flame. The flame all time is a flame. How can I calculate the change?
Yeah, that's right. You can. These points are theoretical. Theoretical points.
But in practice, how can I measure the change of the?
Well, you cannot. In a counterflow flame, the area is changing, but you can't measure it.
I can't measure.
Right. But it is changing. It is a stretched flame.
So you can probably estimate it by the flame getting thinner, no? So given a certain power, you can try to estimate how much larger the flame has become, depending on how much thinner it is.
But it's confusing because in the actual experiment, the flame looks like it has a fixed area. But in fact, its area is changing.
If I want to measure the consumption velocity is the same. Because I have the flame propagates in this direction.
No, I don't think so. I think it's a function of the stretch rate.
Yeah, but if stretch is small,
If it's small, yeah.
I will neglect. I multiply SA by the same velocity. There are no change of consumption velocity.
Well,
so it's strange for me.
This is a theoretical picture of what's happening.
But in practice,
In practice, it may be a little different.
So it's,
Let me ask some question about this equation. If we draw Paul Torrance as just and take into account just K bar and the how to say, no, the sum dt.
Mm-hmm.
I don't remember. How actually, what's the name of this? Sigma. Okay. But we observe some kind of stability. The sigma dt equals K bar sigma. It's
right.
positive. It's some kind of stability.
That's right. That's right. It would be. You would have an exponential solution that would grow in time. If you. That's right. If you put. That means if you had constant stretch. If K was a constant, the area would increase exponentially in time. But it doesn't, and unfortunately it does not, because the flamelets merge. That's the source, the sink term, and they quench if they are stretched too much, and they diffuse, and so they spread out. You signal so, but you're right. If it was just pure stretch, it would always. Now, the last thing I want to point out is that we want to make these measurements useful to somebody, and Menabo and Ponceau have computed this quantity, assuming that every turbulent eddy is an eddy pair that is perfectly aligned to the flow. We can take our data, we can see what the correct number is, and to do that, Adam just pretended he was a LES modeler for a few days, and he took his data and he broke it up into these grids, these cells. He tracked the eddy motion in each cell, so he has thousands and thousands of eddies that move around in this cell. He performs filtering by doing both spatial and time averaging on that cell. And then he correlates the data just like you would for LES. Or if you had DNS, you could do this. But he has the actual data. And so I guess I will sum up by saying that he comes up with a strain rate transfer function, which is very much like the stretch efficiency function. And it's a function of two non-dimensional parameters, the strain rate in the reactance and the size delta here, which is the filter size. So he's done a standard LES analysis, and this is from experiment now, and he has some functions that he fit there. And so now an LES person could then use this as a subgrid model. It'd be very close to the Menabo Ponceau approach, except it's now has experimental data instead of computational data. Okay. To conclude, then, we had to develop a method. We saw different types of wrinkling, Domkohler wrinkling and non-Domkohler wrinkling. Eddies were destroyed. The Landau hydrodynamic instability was seen very often. Strain structures and vorticity were both observed. And we have some measurements. And the last thing I'll say is that what we're doing now is we take this laser sheet and we lay it horizontal, and then these eddies come up through it, and we're attempting to make a three-dimensional measurement. So if we have a spherical eddy and it comes up through the sheet, you will first see a small circle, a big circle, and then a real big circle, and then a small circle, and a small circle, as this sphere goes up. Now, if we assume that the shape of the eddy does not change through the passage, we can apply Taylor's hypothesis, and we can generate these things. And then we have another sheet, a vertical sheet, and we check Taylor's hypothesis using a vertical sheet, which is an approximate way to determine if the Taylor's hypothesis is correct. So that's the work that we're doing now, and I guess I will take about 10 minutes of questions, and then we can go to the next talk.
Equation for sigma. This is some kind of model equation. Yeah? It's not an equation which is derived from the first principles.
Let me think about that. Maybe somebody can help me out on this a little bit.
I have this similar viscosity there.
I think Sebastian Kendall would say that it was developed from first principles.
Each term needs to be modeled.
Yeah, each term is modeled. Yeah, so the convection terms, the unsteady term. In fact, if you put a correlation over if you put a bar over sigma and k, then it's exact. But if you take that bar off, you're making a modeling assumption.
It's a kinematic equation.
This is kinematic.
The
For a
original,
given velocity field. Yeah?
the original equation derived or proposed by Isaac Nobel was kinematic equation. And then Sebastian Campbell put it in the right form
Yeah.
from the fundamental principle.
Okay. In principle, if there is an equation for the form of front, it's possible to consider analytically these processes just deriving equation for two-point correlation function of the form of flame. Of course, original equation is non-linear, so it should be some kind of equilibrium nearby. It's possible to. Somebody did this or not? Just using two deriving equation from the original equation for the two-point correlation function for a given velocity field, like people do in passive scale or in small scale dynamo.
Like a regression analysis or something, where you use the correlations to predict
But
what would happen.
it's impossible to calculate two-point correlation function, not mean field equation. Equation for the second moment of this.
But how do you get the two-point correlation? That's the thing.
If statistics of velocity field is given,
Oh,
it's
yeah,
possible
see,
to
that's
derive this.
Yeah, I've seen some papers along that line, and the problem is the velocity field is made up of discrete vortices,
Yes,
which
of
have a
course.
physical structure, and
Yeah,
so
of
if you try to treat them as a Markov process, some sort of statistic process, you will lose that information. For example, there's a residence time of an eddy across a flame.
You mean if you use Gaussian velocity,
Yes.
Gaussian statistics for velocity? But
Yeah, I think you lose that information. I mean, my understanding is that the G equation is a very, it may be a better or a different way to do it than the flame surface density equation. But my understanding is those two are the main competitors right now. And you know, maybe you can put it in that framework. But those two are the main candidates. Good.
There is a paper in the Russian literature, short paper, exactly looking at
I was wondering, why you want to directly compute production term in this, how do you call it, Kendall equation? Because I think you have all the components, you know N and you know the strain rate, so you can directly compute this production term there, or not?
The ADT over 1 over A. That's you had to show.
No, the KDT.
Okay, but you have that too.
We
You know
we
the
do
flame
compute
position.
1 over a dAdt using the data in one plane. Yeah, we measure, we can compute all the quantities in that.
Yeah.
We call that K, the stretch
Yeah,
rate.
that's one.
Yeah.
But it's not, it doesn't have all the velocity components.
No, okay, but at least in the plane you could do it then.
Yeah. We have done some of that. We have the strain and the stretch. I just didn't show you.
Yeah, okay.
Just continue that. You could take this, the other model, that's this sigma.
Yeah.
That is, you take the time derivative divided by 1 over sigma, it should be the same. Because also it should be the rate of
We don't-
change of the area. D sigma dt and divided by 1 over sigma, it should be the same thing.
It's the same thing as what though?
As to the K that you have.
Yeah. We have not tried to measure the, well, we could measure the flame surface density
Yeah,
signal
that's
as
what I
well from the experiment too. We haven't done that.
So how do you actually determine the surface densities or the surface?
Surface area, yeah. For a similar experiment, sigma is defined as the limit of the area of the flame divided by the volume, the area per unit volume, as delta x goes to 0, where we take a small volume, V, and then we have some area of the flame that's in the volume, okay? So, what you can do, you can, since we have only data in one plane, we say that it's approximately equal to the limit, as delta x goes to 0, of the perimeter of the flame per unit area of the box. So now we have a two-dimensional box. It has a certain area A, which is delta x by delta x. And then we have some perimeter of the flame in there. And if we take this, we get a quantity that we get the flame surface density. We can measure that.
So it has something to do with the fractal dimension somehow.
Yeah.
Okay.
Yes. Yeah. It really is. When you think about this, is the box gets very, very small. The perimeter is about the same size as the box, but it's also, this is the area of the flame in the box when the flame is in the box, and there are many times when the flame is not in the box. So this is really giving you the probability that the flame will be in the box. Okay, so we get sigma as a function of x, and it's really telling you what's the probability, you know, that if you have a flame that's flopping around like this, what's the probability that it's there? And so we can get that from the data, but we haven't done that in this particular experiment. We've done it in other experiments.
Experiments are limited to large scales, so to say, relatively large scales, because you don't resolve. The resolution is about 0.1 millimeter that you have in the pixels.
But the flame doesn't have any scale smaller than that.
And well, if it changes.
Yeah, yeah.
And then you have, it's larger than what you
Yeah,
can see.
when we take the limit of x going to 0, we have to be sure that what we do is we take x to be a small number, and then we try different small numbers and hope to get about the same value.
Jim, I have one question concerning your conclusion. Could you show
Yeah.
the conclusion, please?
Okay.
The first page of your conclusions. In fact, I don't understand the increases, the second line. Increase flame area at 30 times. 30 times. In what sense here? It's a steady flame statistically. It's a statistically steady flame. So what do we mean 30 times?
When we see this interaction, now we're talking about just a small region. When we see a flame, and then later time we see a bigger flame, and when we can measure this quantity K, which is the rate of change.
But how do you determine 30-10? Because for me it's a steady flame. Okay, so you begin to measure from some given time. So it depends on the time you take.
I understand what you mean. It causes a local increase in the flame area in the region we're looking at.
From what time I begin to...
Well, from the beginning of when we see the interaction to the... So, yeah, we should really change this too. It increases the flame area during one interaction at one small box.
If I change the time of observation, is the same conclusion or not? Is it the same conclusion?
The flame will be increased during the beginning of an interaction. But no, at some later time there may be no interaction. Right.
For me it's not clear this.
Yeah, I understand what you're saying. The turbulent flame has a certain area that is fixed. That's correct. So if we integrate it over all times and all space,
I continue my question. In fact, what I don't understand really. In fact, there is some influence of rundown instability.
Yeah.
But how to discriminate when I will have this?
I think we can
What
say
parameter? What
the
parameter?
vortex
check?
creates a wrinkle,
But what parameter? What I can?
a curvature.
But in comparison with what? Because I can.
Radius
I
of
can imagine some
curvature compared
parameters,
to,
patterns.
I think radius of curvature compared to flame thickness. If you have a radius of curvature that is on the same order as the flame thickness, then I think the hydrodynamic instability will dominate. I'm guessing.
I can tell you one thing.
I think so.
For example, we have a very intense turbulence.
Yes.
So we have a very big curvature.
Mhm.
We will have or not rundown instability. Because we have a very small vortices.
Yes.
So the flame can be
Mhm.
extremely curved.
Mhm.
What about rundown instability?
Oh, I think you'd have very strong Landau instability.
Independently of strong or not of the turbulence.
As long as you have very small wrinkles.
Because if we have very intense turbulence,
Yeah.
for me, the rundown instability is, you will be, you can't see this instability because,
Mhm.
yes, it's immeasurable.
But maybe in the equation
So-
for the mean field,
Mhm.
you can continue to consider
I have to think about that.
And the
Both the scale and the intensity.
I continue again. Question, for example, you have very intensive turbulence, okay? And you have the ignition process. So at the beginning, you have even the turbulence is extremely strong. You have the some period of time where we can have a very.
Yeah. I agree with you. I agree with you.
So maybe here in this
Yeah, I
period.
don't know the answer. I think you're right. If we had very intense turbulence, instability might be a minor.
Yes, mine important.
And if the eddies were really large,
Yeah.
then it might have a minor effect too.
But in the initial time of ignition, for example, we don't have influence of.
So this is why we need better models to
Yes.
put all this
Yes,
together.
for ignition process, for example. Even in the very hot turbulence.
But we could, you know, if you have a hypothesis, we can go through the data and just see if the hypothesis is correct, because there may be regions where there's very intense turbulence and there's no hydrodynamic instability. We've only run the experiment for one condition, so, you know, but that's a good thought. Okay, maybe I better stop and take questions later so that Andrea can give his.
We can take a break.
Yeah.